Okay, today we're going to learn about stoichiometry, and stoichiometry is basically the mathematics of chemistry, or a fancy word for saying mathematics or equations involving ratios. And not only can you use it in chemistry, you can use it throughout your whole life. So it's a good skill a good skill to have and learn and master. Okay, so to give you a simple stoichiometry example, let's look at making a pizza. Now, everybody likes pizza. So try to write a simple chemical equation for making a large pizza. So here's a recipe for doing that. We have 2 cups of dough, 1 cup of sauce, 2 cups of cheese, and a half a cup of pepperoni. So if we were to write a chemical equation, we would write 2 cups of dough plus 1 cup of sauce plus 2 cups of cheese plus 1 half cup of pepperoni. Now this should say pepperoni here. Sorry, and then yields 1 large pizza. And then I took out the word cups because it would have made the line too long for the screen. But you could put cups in here to make it exact but it's implied here that these are all cups because I told you up here, right? And then instead of the ingredients, we're going to call these reactants in a chemical equation. Okay, so let's look at our chemical equation for making a pizza and try to make some predictions for making more or less pizzas, or how much ingredients I need to make a certain number of pizzas. So our first question is, if we wanted to make 3 large pizzas, how many cups of dough do we need? Well, if we're going to make 3 large pizzas, then you're just going to say, well, I need to triple everything in my recipe or my chemical equation. So instead of 2 here, I'm going to multiply that by 3, and then my answer should be 6 cups. 6 cups of dough. It's pretty straightforward, and it doesn't take a lot of math to do that because you're just going to triple everything because you're going to make 3 times as many pizzas, and this is the recipe for one pizza. I need to make 3 of these, so I'm going to triple everything. So now it says we have 4 cups of cheese. How many pizzas can we make? Again, we just look at a recipe in here. It says for every 2 cups of cheese, I make 1 large pizza. But now I have 4 cups of cheese. So I'm having 2 times this amount. So I'm going to make 2 times this amount. So I'm going to make two pizzas. So we can make 2 pizzas. And this is nothing that's new to you. You've already do this all the time in your lives. But now we're going to start to focus in on how can we do this with chemistry. So let's go back to our pizza chemical equation again. And now let's answer a couple of questions that will help us focus in on the chemistry aspect. But it's also applicable for other life activities. But we're going to use chemistry as our tool to demonstrate and develop the concept. What is the ratio of cheese to pepperoni? Well, in my chemical equation here, it tells me the answer. I have 2 cheese for every 0.5 cups of pepperoni. So 2 cheese cups for every 0.5 cups of pepperoni. And there's several ways to write this. First way is 2 cheese, and I'm going to abbreviate again with a Z, to every, and you just put a colon, 0.5, and I'm just going to call it pep. That's pepperoni. Or you also could see it written as 2 cheese over 0.5 pep. All right, so 2 to 0.5, 2 to 0.5, 2 to 0.5, right? And that's the ratio. Now, does this ratio look familiar? This ratio would be similar to a mole to molar mass ratio or something like that, but now it's all in moles. So now the next question is, if we have 6 cups of dough, how many cheese pizzas can we make? So we know for every 2 cups of dough, we make 1 large pizza. I have 6 cups. So 6 is 3 times 2, so 3 cups. So 3 times this number. Therefore, I can make 3 times this number. So the answer would be 3 pizzas. And you've done this all in your head. This is nothing new. It's just basically, what's the recipe tell me, right? If I have to triple my recipe, or my recipe's been tripled, I can make 3 times as much stuff for a product, but I'll need 3 times as much stuff on the other side too. So now we're going to hone in a little bit more on chemistry. So instead of using a food recipe, we're going to apply the same techniques to a chemical equation or a chemical process. And so how we do that is, instead of using the word cups of dough and ingredients, we're going to change the word ingredients to reactants or products, and that's these here. And instead of using the word cups that we've implied here, we just didn't write that. Now the coefficients are going to be called moles. And the moles, again, is our unit of measure for the amount of substance in a chemical equation. And so from now on, these coefficients in a chemical equation are going to represent the number of moles. Everything else about the way we treat the moles and the mole ratios and all that is the same as we did for the pizza recipe. So for example, if 2 moles of this makes 2 moles of this, 1 mole of this makes 2 moles of this, I need 2 moles of this and 1 mole of this to make 2 moles of this. Everything else is the same, but we're just changing the terminology. Okay, so now let's apply this to a real chemical equation. I've given you a chemical equation right here. Now notice I've written the number 1 here. Now normally we don't do that. Remember, we leave this blank. It implies a 1. Otherwise you wouldn't have to write anything here. But it's implied 1. But for this particular exercise, I'm putting the red number 1 there. But again, we don't normally list it, right? And now these coefficients, again, are the number of moles of these reactants and products, right? So what is the molar ratio of reactants and products? Again, just like we did before, you just list it. So there's 1 mole of N2 to 3 moles of H2 to 2 moles of NH3. So 1 to 3 to 2. Now some people will just write it this way. You'll see it both ways. I like to write it this way because now I can tell you it's 1 mole of this to 3 moles of this thing. 1 moles of this thing to 3 moles of this thing. Here I have to go back to my chemical equation to figure out what's the 1 and 3. They're always listed in the order that they come in the equation, right? 1 to 3 to 2, 1 to 3 to 2. But I always like to write it out like this for clarity, right? Now, it says here, for every mole of nitrogen, how many moles of ammonia do we make? Well, we just look at our balanced equation. It tells us all the information we know. So it says for every mole of this, here's my 1 mole of this, I make how many moles of ammonia? Ammonia is NH3. I make 2 moles of that. There's no calculation. Just look at it. 1 mole of this makes 2 moles of this, right? For every mole of nitrogen we use, how many moles of hydrogen do we need? Again, look at the balanced equation. 1 mole of this requires 3 moles of this. 1 mole of this requires 3 moles of this. So if we write the answers here, this would be 2 and this would be 3. Now, so the last one has multiple parts, right? So let's look at that, how we were going to answer that one. Suppose we had 2 moles of nitrogen, how much NH3 could we make? Well, you can look at it right now. For every 1 mole I make of this, I make 2 moles of this. So if I had 2 moles of this, I'm going to make double this. So that would be 4. Okay? So 2 moles of this would make 4 moles of this. So the first answer would be 4. 4 moles. Now the second and third answer, we have to do a little bit more math on that one. So it says how many moles of H2 and N2 would I need to make 1 mole of NH3? Well, we're looking at our equation here, and he says for every mole of this, I make 2 moles of this. But I only want to make 1 mole of this. So how do I get 1 mole of this? Well, I'd have to divide everything by 2, and we could do that. We could just put a little 2 underneath. And don't forget, we have to divide everything by 2, not just one thing. So if we did that, right, it says here, now the question is, how many moles of H2 and N2? Right, well now we can look at our balanced equation again. We haven't changed the ratio because we've divided everything by 2. So now this becomes a 1, right? 2 divided by 2 is 1. And instead of being 3, this is 3 divided by 2, which is 1.5. So I would need 1.5 H2 moles. That's a 5, that's not an 8. And then I'd also need 0.5 N2 moles. And you can see that right here, and it makes sense, right? I'm making half of this, I need half of this, and I need half of this, right? So instead of 2 moles I'm making 1. I only need a half of that, which is 1.5. I need only half of that as 0.5. So again, everything is the same. We haven't changed any of the ratios here. It's all about ratios. So suppose I gave you a number that wasn't easy to do in your head by looking at it, like 3 times this or 2 times that, or I want to make half of that. Or suppose I gave you something that's a little bit more challenging, and it's not a whole number. Let's say it's only 7.17 more times, or I want to make, instead of 1 mole, I want to make 29,602 moles, right? So we have to have a real mathematical way of doing this, and we already do. We have the factor label method, and that we use for the mass mole particle activities. But now we're going to use the same technique for the ratio. So again, let's just look at a simple problem here, right? And here's the general equation. Let me just give you the general equation first. You're going to use the given amount in moles, right? So what I tell you, or what the question asks for, again, put that over 1. Now here's where you're going to use your molar ratio from your balanced equation. And again, you're going to put the moles of the given substance on the bottom and the moles of the desired substance on the top. And that would be one of these numbers here. That would give you the moles desired product. Let's see how this works. So how many moles of NH3 can I make if I have 0.65 moles of N2? All right. So now I know that for this equation I need 1 mole of this to make 2 moles of this, right? But I'm only given 0.65 moles of this. So I'm going to make less than 2 moles of this. So let's see how we worked it. So we took 0.65 moles of N2 because that's what we were given. Again, I put it over 1. Now I'm going up to my equation here, and it says for every 1 mole of N2 that I have, I make 2 moles of NH3. Again, we're looking for NH3, so that has to go on the top. The 1 mole of N2 is on the bottom, so the moles of N2 can cancel. And now, when we do the math, it's 0.65 times 2, which is 1.3, divided by 1 times 1, which is 1, and we get 1.3 moles of NH3. I didn't really do much math in this, right? Everything else is the same that we've done before, except now I've used the factor label method, right? And my ratio that I've been talking about is this ratio here, gotten right from the balanced equation. I didn't have to do any calculations. I didn't have to look anything up. I didn't have to do anything like that, like we had done in the particle one, where you had to maybe look up or calculate the molar mass. The ratio here you got right from the equation. Okay, so now let's apply this to a real chemical equation. Now we showed you with the pizza example how we get the ratios, and then we told you that instead of using cups, we can now make the coefficients moles, and we know that these are all the moles of reactants and products in this chemical equation. So now the question becomes, how many moles of H2 do I need to make 0.4 moles of NH3? And now we're going to use the factor label method, or the method we've been using in class. So if we just put 0.4 here, because that's what I'm given, and it's NH3, so moles of NH3, right? And we put that over 1. Now it says I'm looking for the number of moles of H2. So I'm looking for H2. So I'm going to go back to my chemical equation. I'm going to multiply my thing. Now I need to have moles of NH3 on the bottom here. So we already have that known. You don't have to even think about it. You just write moles of NH3. All right. And now here, we don't have to do any calculations. We just have to look at our balanced equation and use this number here too. So with that number here, 2. And now what are we looking for? Hydrogen. So we're going to look at our chemical equation. It says 3 moles of hydrogen. And we just put 3 moles of H2. And then we said equals. And if you do the math here, you get 0.6 moles. All right, and now that makes sense because if you look at this really closely, right, I'm only starting out with 0.4 moles of this instead of 2. And that's 1/5 of that. If you're quick on the math, you could do that, right? So it's going to be less than 1. It's less than 0.5, which is 4 times less. So it's going to be much less than 1 on this one. 1 on this one too. And the ratio here tells me that it's going to be 1.5 times whatever this number is. And so that's a quick check if you could do that. Now the last question is how are we going to do this with if I gave you something with a little bit less easy number to do in your head. So again, we just do the same thing. We're given 4.23 moles of H2. So we just write that down and we put that over 1. And then it says how many moles of N2 we're going to need. Now, don't forget, again, we need to put the H2 on the bottom here, so we'll just do that right quick. H2, and then moles. And it says here we need 3 of those. And then if I want to have 1 mole of, how many moles of N2, so moles of N2, that's what I'm looking for, that's always on the top. And it says for my chemical equation I need 1. And then if you do the math here, you get 1.41 moles of N2, right? And you can see that makes sense because according to my ratio here, this is 1/3, and it's 1/3 of this number, and that looks close to that number, right? And so that would make sense, right? Now let's look at the next part, which is how much NH3 do I make, right? So again, we start out with 4.23 moles of H2, and then we put that over 1. And now I go back to my ratio thing again for my balanced equation, and I see that I have 2 moles of NH3 for every 3 moles of H2. And again, we have to write 3 moles of H2 on the bottom, because again, H2 is here, and then we write 2 moles of NH3. And then when we do that math, we get 2.82 moles of NH3. And again, to double check your answer, does it make sense, right? So if I'm starting out with 4.23 moles of H2 here, according to my ratio, if I've done it right, I should make 2/3 of of that amount in NH3 form, because it says here for every 3 moles here I only make 2 moles of this, so that's my ratio there. And 2.82 is exactly 2/3 of 4.23. So you know you're in the ballpark if you can see that. Okay, at this point in the lesson, you're going to now do it on your own, right? So I've given you a balanced equation on the top of the paper, and I've asked you about 7 questions here regarding the information from that balanced equation. You don't need anything besides the balanced equation to do your calculations, right? So you're going to stop the video in a few seconds, answer the questions, and then when you're ready to get the answers, start the video and check your answers. So when you are ready, stop the video now. So here are the answers, and some of you may say, well, why didn't you write the FeO2 and Fe2O3 here like you did before? And I would have, but I ran out of space. So technically you could have written it just like this. For this, these are the colon, this is the colon, right? And that would have been the same thing. So these are colons, right? And that you could have used that answer for here. So that's perfectly fine. Everything else is fairly straightforward. If you got all these right, congratulations, you've mastered the first concept part of this stoichiometry chapter. If you struggle a little bit, are still flipping the signs or getting the ratios mixed up, come find me or ask questions in class tomorrow when we meet. But other than that, that's the end of the assignment.